This is the first infinite series for pi ever discovered, and it was found by the Indian mathematician Madhava around the year 1400 CE. Though most of Madhava's original work was lost, so this result was actually rediscovered by the European mathematicians James Gregory and Gottfried Leibniz. And they were able to find this in the 1670s. And in this video, I'll show you a proof that's based off of what James Gregory found. So to start, we need to look at an infinite geometric series. So we have 1 plus a squared plus a to the third power plus a to the fourth power, and so on. This is infinitely long. And let's say that this adds up to some value, which we'll call s. And there are conditions for which values of a that this would actually add up to some value. If we had a is equal to 5, then our sum would be 1 plus 5 plus 25 plus 125 plus 625, and so on. And since every term is getting bigger and bigger than the last term, it's clear that this sum would approach infinity, or in other words, the sum diverges. But if we have a is equal to 1/2, then our sum would be 1 plus 1/2 plus 1/4 plus 1/8, and so on. And as we'll see soon, this sum actually reaches a value, or in other words, it converges to the number 2. So this sum, s, is only valid when a is less than 1 and it's bigger than -1. So now I can take this sum and multiply it by a. So I have a multiplied by s, and I have to distribute the a to each one of these terms here. So I'd have a plus a squared plus a to the third plus a to the fourth, and so on. And the reason I do this is so that I can subtract a times s from s. So we have s minus a times s. And if we subtract this bottom sum here from this top one, notice that the bottom sum does not have a 1, so we'd have 1. And then we have a minus a, so they cancel. A squared minus a squared, and they cancel. A cubed minus a cubed, and they cancel, and so on. Every single one of these terms, other than 1, will cancel out. So s minus a times s is simply equal to 1, and from this, we can solve for s. If I factor the s out, I have s times 1 minus a is equal to 1, and therefore s is equal to 1 over 1 minus a. And notice that if I have an a value of 1/2, and I plug this into this formula, I'd have 1 over 1 minus 1/2, which is equal to 1 divided by 1/2, and that is equal to 2. So this is indeed correct. So I'll rewrite this result in some more free space. 1 over 1 minus a is equal to 1 plus a squared plus a to the third, and so on. And now I can make a substitution that a is equal to minus t squared, so that the sum becomes 1 over 1 plus t squared, and this is equal to 1 minus t squared plus t to the fourth minus t to the sixth plus t to the eighth, and so on. And with this, I can integrate each side with respect to t, so that the integral from 0 to x of 1 over 1 plus t squared dt is equal to the integral from 0 to x of this infinite sum, 1 minus t squared plus t to the fourth minus, and so on, dt. And with the right-hand side of this equation, I can just integrate term by term, so that I get t minus t to the third over 3 plus t to the fifth over 5 minus t to the seventh over 7, and so on. and I have to evaluate this between 0 and x, and the left-hand side is simply equal to the arctangent function of x. And the way to verify this is by taking the derivative of the arctangent and showing that it is equal to 1 over 1 plus t squared. And I'll show this to you over here. So I have the arctangent of x, and let's say this is equal to y. So I'm looking for dy over dx. And I can rewrite this equation as x is equal to the tangent of y. Notice that if I take the inverse tangent on each side of this equation, I'll end up with my first equation. And with the second equation, I can take the derivative of x with respect to y, and the derivative of the tangent with respect to y is the secant squared of y. You can verify this by noting that the tangent is just the sine of y over the cosine of y, and using the quotient rule to find its derivative. And remember that the secant squared of any angle is equal to 1 plus the tangent squared of that angle. And this comes from the Pythagorean identities. And notice that x is equal to the tangent of y. And here we have the tangent of y squared, so this is really just equal to 1 plus x squared. So dx over dy is 1 plus x squared. And if I take the reciprocal of each side, I'm left with dy over dx is equal to 1 over 1 plus x squared. And this is the derivative of the arctangent function. And it does indeed equal 1 over 1 plus x squared, which is what we were looking for. So now I can evaluate this right-hand side between 0 and x, so that the arctangent of x is equal to x minus x to the third over 3 plus x to the fifth over 5 minus x to the seventh over 7, and so on. And this lower bound here is 0. When I plug that in to this formula, I would just get 0, so I can ignore that. And I should note that this formula for the arctangent, which you might notice is the Taylor series for the arctangent function, is only valid when x is less than or equal to 1 and greater than or equal to negative 1. And if I just set x equal to 1, then I have the arctangent of 1, which is 1 minus 1/3 plus 1/5 minus 1/7, and so on. And the arctangent of 1 is like having a triangle, or let's say this angle is theta. So the arctangent is equal to theta, and the ratio of the opposite to the adjacent side is 1. So we could say that this side, the opposite side, has a length of 1, and the adjacent side has a length of 1. So we need to figure out what this angle theta is when this ratio is 1. And theta is simply 45 degrees, or in radians, this is pi divided by 4. So this whole infinite sum is equal to pi divided by 4. And this is the first infinite series for pi ever discovered.